Hey all, welcome back. This is going to be 4.5, but we're actually splitting 4.5 into two separate sections because stoichiometry, and it's been a while since we've maybe done stoichiometry, so I want to make sure we review it and get it pretty solid. So remember, if you need to read about this covers 4.3 and 4.4, so we're going to have like an introduction to stoichiometry, and then we'll talk about limiting reactants, all kind of in the same little situation. Our homework is right on there. And so let's kind of just jump right in. So this is 4.5 and this is part 1. Now, real quickly, these steps right here will work for all stoichiometry. These steps never change, all right? So they're kind of your go-to when doing a stoichiometry problem. So our first step, we have to write that balanced equation, which is why the previous part has been so important. All right, our next step is we need to find moles. So there's a couple of ways that we can find moles. And today is going to be our focus grams to grams, all right? But from grams to find moles, we will divide by the molar mass. All right, so that's from there. To find moles from gaseous volume, you can either use PV equals nRT, all right, and find moles that way, or you could use the molar volume. 1 mole equals 22.41 liters, all right? But this one has to be at STP. And again, not really our focus today, but I feel like we should put it on there. All right, and then from molarity, we're going to use our molarity equation. All right, moles over liters. All right, then we're going to do our multiple ratio to find our unknown, to find grams. We will multiply by molar mass. All right, to find gaseous volume, again, we could use PV equals nRT if we're not at STP, or we can use 1 mole equals 22.41 liters. And this has to be at STP again. All right, and then to molarity or liquid volume, again, we use our molarity equation, moles over liters. And again, this will actually be 2 videos down the volume one, the liquid volume. All right, so let's kind of just review by doing a quick little problem here. So we've got, during photosynthesis, plants convert carbon dioxide and water into glucose according to that equation. So here's our equation. Now, suppose our particular plant consumed 37.8 grams of CO2 in 1 week. Assuming that there's more than enough water present to react with all the CO2, what mass? So we're looking for mass of glucose. All right. Can we synthesize? So if we keep rolling here and get into it, our first step is to write a balanced equation, which we have already up here done for us, okay? Our second step is to convert to moles, and we'll find moles by dividing by the molar mass. I honestly like to put this all on a handy-dandy T-chart. That way we can do all of our calculations right at the end. So we have 37.8 grams of CO2. All right. And again, we're using that T-chart. And so we're going from grams to moles. To do that, we're going to divide by the molar mass. Well, CO2's molar mass, 44.01. All right, grams per mole. Remember, we found that just kind of as a side. We took C1 times 12.01. We took O2 times 16.00. This is 32. This is 12.01. We added those up. We got 44.01. That's our quick review of finding molar mass. Hopefully you remember that, because if not, you need to probably head back to that first unit that we did. All right, so we've got 44.01 grams of CO2, and we've got 1 mole of CO2 on top. So this is about our unit canceling. Our next step is where we use the balanced chemical equation. We're going to figure out, for every 6 moles of CO2, I form... This should just be O2 right there, just so we have that. I form 1 mole of C6H12O6. All right? So moles canceled, grams have canceled. All right? And so since we're going to grams of glucose, we're going to do that same thing. All right? We're going to take 12 times 6 plus our 12, and then plus So we should get around 180, like 180.1, all right? Or something very close to that. All right, and remember to solve these t-charts, we multiply across the top, divide by what's on bottom. So I'm going to take that 180.1, take it times 37.8, and then I'm going to divide by 44.01, and then divide by 6, and this should give me my answer. So I form 25.8, make sure I read that right, 25.8 grams of glucose in 1 week from this plant. All right. Okay. Everybody good with that? Awesome. So that was a quick review on mass-to-mass stoichiometry. Now let's throw in our limiting reactants and excess reactants. So remember our limiting reactant. How about this? Let's think of this. We're going to make a grilled cheese for the class. All right. Everybody gets grilled cheese. I brought a loaf of bread, a thing of Velveeta, and like a big old tub of butter. All right, what am I probably going to run out of first? Hopefully you said bread, because that's probably what we're going to run out of first. Even though our class is small, if we want seconds, we're probably going to run out of bread first. So our bread limits how many grilled cheeses we can make, right? So limiting reactants is what stops the reaction. All right? Because I can't make any more grilled cheese. I can't just throw cheese on the griddle and call it grilled cheese, right? Technically it would be grilled cheese, but I don't think it'd be very good. All right. So it stops the reaction. So this limits how much product we can get, right? That's the reason limiting reactant. Then we have our excess reactant, and this is the one that is left over at the end. So like if I didn't eat butter at all, I would just have that butter left over for days on end until I could make more grilled cheese. All right. Then we have our percent yield, and this tells us how well a reaction went. Okay, so this tells us how well our reaction went. Did we do well? Did we not do well? Our formula there is actual, like what we actually got, over what we should have gotten, which we call theoretical, and then times 100. So it's just like maybe your grade on a test. You wanted to get, or you got 70 out of 100, so your percent was 70%. Maybe not good, maybe good, depending on what you got. So let's check out how to do this. The steps are exactly the same as stoichiometry, so it's not any different. We just have to do some comparison to figure out our limiting reactants. So our first question here says, we are starting with 86.3 grams of NO and 26.5 or 25.6 grams of H2, we're finding our theoretical yield. But this has some steps here. We have to figure out our limiting reactant first, and then we can figure out our theoretical yield. Okay? So let's go ahead and start. Kind of as a quick aside, we've got our molar mass of NO. So we've got 14 plus 16, which gives us 30, right? And it's 14.0067 plus our 16, right? So we're going to go right at 30 there. So NO's molar mass is going to be 30 grams per mole. And then we've got H2, let's say 2.018, all right, 1.00794 will give us that, all right. So now we've got those. We're also going to find ammonia eventually. So ammonia is NH3. We're going to go 17.01 grams there. That's 1N plus our 3 H's. Okay, so let's start here by finding our limiting reactant first. So we're going to take 86.3 grams of NO. We've got our balanced equation. So our next step is to figure out moles, and we do that by dividing by our molar mass. So we've got 30 grams of NO, and we've got 1 mole of NO. All right, now we look to our balanced chemical equation. For every 2 moles of NO, I need 5 moles of H2. All right, that's our mole to mole ratio, and our moles cancel there. All right, now we say 1 mole of H2 has a molar mass of 2.018. All right. And now we're ready to calculate. This is going to tell us how much, if we react all of our NO, how much H2 we need. Then that will in turn tell us our limiting reactant. So we got 86.3 times 5 times 2.018, and we're going to divide that by 2 and divide by 30. So if I react all of my NO, I need 14.5 grams of H2. I have 25.6 grams of H2. So first off, we're going to say NO is limiting. It is the thing we're going to run out of first. All right, NO is limiting. That's our first step. Even though that wasn't really asked in the problem, that is what we've got. If this question asked how much excess reactant was left over, we would take 25.6 minus our 14.5, and that would tell us how much is left over. All right, but it didn't ask that, but just helping you for future problems. Okay, so since NO is my limiting reactant, we can't use this 25.6 grams of H2 anymore because we know we have excess. So we'll go down here, 86.3 grams of NO. We're always going to use our limiting reactant to do further calculations. All right. So same first step, 1 mole of NO. We've got 30 grams of NO. Okay. Now our mole-to-mole ratio, we still have 2 moles of NO. And this time, it's for every 2 moles of NH3. And then our last step is to multiply by the molar mass, 1 mole of NH3. And then we have 17.01 grams of NH3. And again, we'll multiply across the top, divide by the bottom. So 86.3 times 2 times 17.01 divided by 2 divided by 30. Okay, this gives us, we form 48.9 grams of NH3. This is how much we should have gotten in theory. All right, what we did get would be what we measured in class, all right, or in the lab. Okay, awesome. Hopefully that works for us. Let's do one last problem and call it a day for our gram to gram. Okay, so here's our next problem. We have 28.6 kilograms of C. Reacts with 88.2 kilograms of TiO2. We form this much Ti. This is going to be our actual. All right. Find the limiting reactant, theoretical yield, and percent yield. All right. Woo, we got some work ahead of us. All right. Since all of them are in kilograms, we can actually just leave that in kilograms. Because they are proportional, okay? But we do need to do an aside and figure out our molar masses. So let's do that in purple, kind of over here. C, really easy, 12.01, right? We have TiO2. All right, we've got 2 O's at 16 times 2. And then we need to add our Ti, which is 47.867. So our TiO2 is 79.87. And that's grams per mole. Grams per mole. And then our Ti, right, should be really easy. It is 47.867. All right, those are the ones we need for our problem. We were just kind of getting that out of the way early. Okay, so here we go. Let's jump in. We could start with either of these. We could start with carbon and go to TiO2, or we could start with Ti2 and go to carbon. It really doesn't matter. So let's just for funsies start with TiO2. So we've got 88.2 kilograms of TiO2. All right. And again, we're converting that to grams of C. All right. First step, divide by our molar mass of TiO2. So we're going to divide by 79.87. And that's grams of TiO2, 1 mole of TiO2. And now we're ready for our mole-to-mole ratio. All right, our mole-to-mole ratio, for every mole of TiO2, I have 2 moles of C. All right, moles of TiO2 cancel. And then we go 1 mole of C has a molar mass of 12.01 grams C. All right. And let's see what we get there. 88.2 times 2 times 12.01 divided by 79.87. And this would be 26.5 kilograms of C. This is how much C we need. Ooh, we have 28. So it looks like we have just barely enough. All right. So we know that TiO2 is my limiting reactant. All right. This one we're not going to use. So let's figure this out. We're going to do the same step, 86.2 kg TiO2. And we're going to take that, boop, all right, to, this time we're going to go to Ti, so our same first step. All right, and then our next step is still very similar, except this time we've got 1 mole of TiO2, and we're going to put 1 mole of Ti on top. And last but not least, we're going to say 1 mole of Ti has a molar mass of 47.867, and that's grams of Ti. Moles of Ti cancel, moles of Ti, yep, we're all canceling across the board. So to multiply, we're going to take 88.2 times 47.867, and we're going to divide by 79.87. And this is going to give us 52.9. This is kilograms. My apologies. This is kilograms. Boop. Kg of Ti. This is how much we should have gotten. In theory, if we did this, this is what we should have gotten. All right, but what we got was this 42.8. So to figure out how well we did, we're going to take 42.8 divided by 52.9 and times that by 100. This will tell us how well our reaction went. 42.8 divided by 52.9 times 100. 80.9%. That's not terrible. All right. So we have an 80.9% yield. Awesome. See you next time.